Welcome to our video lecture on solutions and concentration. Our objectives for today, we are going to define and describe solutions, solutes, and solvents. We're going to define soluble and miscible. We're going to describe factors that affect the rate of dissolving, and we're going to review how to use the solubility tables. And then we're going to get out our handy-dandy calculators, define and calculate molarity, molality, parts per million, and parts per billion. We're going to look at percent by mass and percent by volume, all different ways to calculate and measure concentration of solutions. And then we're going to look at how to define and then calculate concentrations of diluted solutions. First up, some definitions. A solution is a homogeneous mixture. This means that it is same throughout. So remember that we talked about mixtures as being homogeneous or heterogeneous. We're talking about same throughout mixtures in which one substance is dissolved in another. A solute is the thing that is being dissolved, and then a solvent is the substance that is doing the dissolving. So if I have a solution of salt water, the solute would be the thing that is being dissolved, that would be the salt. And the solvent is the thing that is doing the dissolving, that would be the water. Solvation is the process of dissolving. When we have a crystal of salt, sodium chloride, what happens is this: the negatively charged chloride ions are attracted to the positive side of a water molecule where the hydrogens are. The positive side of those hydrogens is going to surround these negatively charged anions of chloride until there's like a bubble that surrounds the whole entire thing, and then those anions can float freely around in those water molecules. Solubility is the amount of a substance that will dissolve in another. Soluble generally means that something will dissolve. Salt dissolves in water, so you would say that salt is soluble. Insoluble things won't dissolve. Gold, not super soluble in water. These words, soluble and insoluble, we tend to use just with solids. If we're talking about liquids that will or won't dissolve in each other, then we're going to use the vocabulary word miscible instead. So if a liquid will dissolve, then it is miscible. Vinegar dissolves pretty well in water. Vinegar is miscible in water. Immiscible, it will not dissolve. Oil is immiscible in water. Our general rule about solubility is that like dissolves like. So polar things are dissolved by other polar things. Nonpolar things are dissolved by other nonpolar things. Polar and nonpolar compounds generally don't dissolve each other very well at all. Let's talk a little bit more about what this thing polar even means. So water is one of the most magically polar substances around. What makes water polar is this: electronegativity differences. Remember that electronegativity is the pull that elements have on shared electrons in a covalent bond. So there are some electrons here being shared between hydrogen and oxygen, but oxygen pulls on them more strongly. So the electrons hang out closer to the oxygen side of the water molecule. They spend less time over here on the hydrogen side of the molecule. That makes oxygen partially negative. This is lowercase delta. We use it to show that the oxygen side of this molecule is partially negative. The hydrogen side of the molecule is partially positive. What that means is this: hydrogen bonds can form between those water molecules. The negative side of an oxygen molecule, the hydrogen positive side of another water molecule, are going to be attracted to each other because we know opposites attract. Positives and negatives, there's an electrostatic force of attraction here between the hydrogen and the oxygen because a little bit of positive and a little bit of negative. Because water is so beautifully polar, it dissolves lots of polar things, lots of ionic things, and so we're going to call it the universal solvent. It doesn't actually dissolve the whole entire universe, but it dissolves a lot of things. And then the solutions in which water is the solvent, those are called aqueous solutions. Other molecules and compounds that are polar like water dissolve really well in water. How do we know if something's going to dissolve in water or not? Remember that in our handy-dandy reference materials on the back side of our periodic tables, we have our solubility of common ionic compounds in water. This table is between your list of polyatomic ions and your activity series. So we're going to use this table to figure out if things are soluble or not. Sodium chloride. I'm going to find chloride here. I see that it is in my soluble list. I go over to the exceptions. Sodium is not an exception, so this will dissolve. I would say that it is soluble. How about lead 2 iodide? Iodine is here. I look over, lead is actually on my list of exceptions. So even though iodine usually will dissolve, because that lead is an exception, it will not dissolve. So this guy is insoluble. How about magnesium hydroxide? Hydroxide's way down here. It is insoluble except if it is with ammonium. Alkali metals, remember this is group 1, so lithium, sodium, potassium on down. Calcium, strontium, and barium. Magnesium is not on this list, so this is insoluble because hydroxides are not soluble unless they're on the exception list. How about calcium hydroxide? Still here looking at hydroxide, but notice that calcium is on our exceptions. So hydroxides won't dissolve except when they're with calcium, and so this actually is soluble. It will dissolve. These are the last two I want you to do on your own here in Edpuzzle. All right, quick check on answers. Hopefully you decided that sodium carbonate is soluble because even though carbonate is insoluble, alkali metal cations like sodium will make it actually an exception to insoluble, which makes it soluble. Sodium carbonate is soluble. How about calcium carbonate? Looking at carbonate still here, notice that there is not a calcium on the exceptions, and so calcium carbonate insoluble, sodium carbonate soluble. Solubility is actually affected by quite a few different factors. Some of the factors that we're going to focus on here that affect how much of something can dissolve are temperature and pressure. So temperature kind of makes sense, right? If you have some sugar and you're trying to dissolve it in your coffee, you can get more sugar to dissolve in your hot coffee than you can in your cold coffee. That sugar will just settle down to the bottom of your cold coffee cup, which is why sometimes we heat up the coffee, add the sugar, and then let it cool off so we can keep that sugar dissolved in our coffees. Pressure is another one that affects how much stuff can dissolve. So if I am squeezing together my sugar in my coffee, that force of pressure actually pushes that sugar into a crystal shape. So solid is easier to be highly pressurized than it is to be a liquid. And so pressure, we're actually going to dissolve fewer solids. But here's a crazy thing. What if I'm trying to dissolve like carbon dioxide bubbles in my Dr. Pepper? So if I'm dissolving a gas in a liquid, then an increased temperature is actually going to decrease how much gas can be dissolved in my solution. You know this because warm Dr. Pepper goes flat. Fewer carbon dioxide bubbles can be dissolved in our liquid Dr. Pepper when it gets warm. So the higher the temperature, the more those gas molecules move around, the fewer of them will stay dissolved in our solution. Pressure is the opposite. So the higher the pressure, the more of that gas we can keep dissolved. And we know this also because Dr. Pepper, whoa, that was supposed to be a bottle of Dr. Pepper. Let me try again. How about this? Here's the cap. Here's okay, maybe, all right, we'll pretend like this is Dr. Pepper. If we keep the cap on, then we know that those bubbles of CO2 will stay inside our Dr. Pepper. But if I take the cap off, all my gas bubbles will leave my solution. We're going to have fewer gas bubbles dissolved if the pressure is decreased when we take the cap off. So these are factors that affect how much of something can be dissolved. We also have factors that can affect how quickly we can dissolve stuff. So of course, agitation, shaking, stirring, swirling will make things dissolve a little bit more quickly. And then surface area will also help speed things up. So if I have a cup of water and I throw in 1 chunk of rock salt, it's going to take longer for that to dissolve than if I have a cup of water with lots of tiny salt crystals dissolved. More surface area, smaller pieces, faster dissolving will happen. So molarity is how we measure the concentration of a substance. We're going to divide the number of moles of the solute by the liters of the solution. This is not a formula that you need to memorize. It is on your handy-dandy periodic table list of formulae. So molarity is here. Molarity is measuring concentration of a solution, moles of the solute, the thing that's being dissolved, liters of the whole entire solution. So this isn't just the solvent, it's the whole entire solution all added up together. So moles divided by liters. Let's practice. So if I have 2.3 moles of sodium chloride dissolved in 0.45 liters of solution, I'm going to divide my moles of solute by my liters of solution. So molarity, and we use big M for molarity. Molarity will be moles over liters. I have 2.3 moles, and we have 0.45 liters. So all I have to do is divide here. Handy dandy calculator says 2.3 divided by 0.45 gives us 5.1111. So many ones. Let's check our sig figs. Looks like we get to keep 2 because I have 2 here and 2 here. So I'm going to keep 2 sig figs. That 1 does nothing to that 1. My final answer will be 5.1, and our unit label is big M for molar. Good, 5.1 moles per liter, 5.1 molar. Do this one in Edpuzzle. Answers here, 1.2 moles over 1.22 liters of solution. 1.2 divided by 1.22 gives us 0.9836. Lots of digits. We're going to keep just 2 sig figs. 1, 2, that 3 leaves that 8 and 8. Final answer, 0.98, unit labeled big M for molar, moles per liter. All right, let's look at these two problems a little bit trickier because now instead of having moles, I have grams, and I can't put grams into my formula. We need to turn our grams into moles. So if I have 98 grams of sodium hydroxide, sodium is Na. Hydroxide is one of our polyatomic ions. It's an OH. Sodium has a charge of +1, hydroxide has a charge of -1. These guys balance each other out perfectly. So I have 98 grams of sodium hydroxide. Turn those grams into moles using the molar mass. So sodium is 22.990 plus 1 oxygen, 15.999, plus 1 hydrogen, 1.008, gives us a grand total of 39.997 grams per mole. I have grams here on the top. I want grams to go away. We're going to put grams on the bottom and moles on the top. 39.997, 39.997 grams on the bottom, 1 mole on the top. We're going to cancel out grams top and bottom. Handy dandy calculator says that 98 times 1 divided by 39.997 equals 2.450, lots of digits, moles of sodium hydroxide. I'm going to divide that by the liters. Now that I have moles, I can go ahead and divide by liters. 2.2 liters of solution. 2.45 lots of digits divided by 2.2 liters gives us 1.1137 lots of digits. Now let's do a sig fig check. I've got 2 here, I've got 2 here. I get to keep 2 sig figs in my final answer. 1, 2. That 1 leaves that 1, a 1, and my final answer is 1.1 big M for molar. You get to do this one on your own in Edpuzzle, not Nearpod, Edpuzzle. Turn your grams into moles, and be careful, you have milliliters here. You need liters. All right, 1.2 grams of HCl. Hydrogen is 1.008 plus chlorine is 35.453. Gives us a grand total of 36.461 grams per mole of hydrogen chloride. Hydrochloric acid, 1.2 divided by 36.461 gives us 0.0329 lots of digits, moles of HCl. I also need to convert my 25 mils. 25 mils of solution need to be in liters. We have to have liters. So we know that there are 1,000 milliliters in 1 liter. 25 divided by 1,000 is 0.025 liters. I'm going to take these moles and divide by these liters. 0.0329 divided by 0.025 gives us a grand total of 1.3 big M for molar after we check and keep only 2 sig figs. Good? All right, let's do some more. How many grams of potassium carbonate are needed to make 200 milliliters of a 2.5 molar solution? This question is different because instead of solving for molarity, we're actually given the molarity and we're given a volume. We need to solve for moles so we can turn those moles into grams. But we're going to use the same formula. We're just going to set it up a little bit differently. Of course, I need to turn my 200 milliliters into liters, divide by 1,000 milliliters in 1 liter. Final answer, 0.2 liters. So I'm going to plug 2.5 molar into the molarity part of my formula. I don't know what the moles are yet. I'm going to leave that as my variable, x moles. On the bottom, the liters of my solution, I turn my milliliters into liters. That's going to be 0.2 liters. So now to solve for x, I'm going to multiply both sides by 0.2. Oops, let me move that decimal place. 0.2, not 0.02. So that cancels out here. When I multiply here, 0.2 liters, 0.2 times 2.5 gives us 0.5. 0.5 equals the number of moles of potassium carbonate that we need to dissolve in order to make this solution. So 0.5 moles is almost our answer, but I need grams, not moles. So we're going to take those 0.5 moles of potassium carbonate. To get to grams from moles, I do need a balanced formula. Potassium is K, it has a +1 charge. Carbonate is one of our polyatomic ions. It's on our list of polyatomic ions. CO3 with a -2 charge, -2 + 1. I need 2 potassiums to balance this out. So 0.5 moles of K2CO3. Convert that into grams, put moles on the bottom, put grams on the top. 2 Ks, 39.098 times 2, 39.098 times 2, plus 1 carbon, 12.011, plus 3 oxygens at 15.999 a pop gives us 138.204 grams per mole. Moles on top and bottom cancel out, and we are left with 138.204 times 0.5. We need 69.102 grams. Let's do a sig fig check. Oh my gosh, we only get to keep one sig fig. There's only one sig fig here, so that 9 is going to round that 6 to a 7, but I need to keep it in the tens place, so my final answer will be 70 grams of potassium carbonate are needed to make 200 milliliters of that 2.5 molar solution. Good? All right, same thing here. You go ahead and set this one up yourself. We're solving for liters. You're given molarity and you're given grams. Remember, you've got to turn your grams into moles, plug your molarity in here, and solve for liters of solution. All right, so hopefully you put this guy in for molarity, so 0.75 moles is going to equal moles of solute. You have grams of solute, so we have to turn our 75 grams of lead to oxide. Lead is Pb, it has a +2 charge because that Roman numeral says so. Oxygen is O, it has a -2 charge. We're golden right here. So lead is 207.2 plus oxygen 15.999 gives us 223.199 grams per mole. Put grams on the bottom because I want grams to cancel out, top and bottom. 75 divided by 223.199 gives us 0.3360, lots of digits, moles of lead to oxide. I'm going to put that on the top, 0.3. I'm going to round my 3 to a 4 since that 6 is there, 0.34 moles of lead oxide divided by, I don't know yet how many liters of solution. So I'm going to multiply both sides by x. So now I have 0.75x equals 0.34. Divide both sides by 0.75 to solve for x. And x is going to equal 0.34 divided by 0.75 gives us 0.34 4, 5, lots of 3s. But when I do a sig fig check, we're just going to keep 2 sig figs, and so my final answer will be 0.45 liters of solution is what we can make using those 75 grams of lead 2 oxide. Good? All right. So molarity is definitely the most common way that we measure concentration, but it's not the only way. So we're going to take a look at some other ways to measure concentration super quick. Molality is almost the same as molarity, but except there's an L instead of an R, right? So molality is moles of solute. That's the same as molarity, but instead of liters of solution, we have kilograms of solvent. So this is what makes molality different from molarity. Molality is not a formula that's on your formula chart. So if I ask you about molarity, I will give you the formula. If I ask you about molarity, you need to use your handy-dandy periodic table. So let's say that we've got moles of solute and kilograms of solvent. Let's see what we've got going on with this practice problem. What is the molality of a solution, which we've got 58.4 grams of sodium chloride dissolved in 1,000 grams of water. First up, I need to turn my grams into moles. So sodium chloride is going to be sodium 22.990, chlorine 35.453, and that's going to give us a grand total of 58.443 grams per mole. So 58.4 grams of sodium chloride, put grams on the bottom, 58.443 grams per mole. Do that division, 58.4 divided by 58.443. This should be pretty equal to 1, and it is 0.999, 0.99925, lots of digits, moles of sodium chloride. And then I have 1,000 grams of water. I need to turn those grams into kilograms. 1,000 grams divided by 1,000 grams in 1 kilogram, and we have 1 kilogram when those grams cancel out, top and bottom. So I've got 0.999 moles of sodium chloride divided by 1 kilogram of water. Our molality will be 0.999 little m. But when I check my sig figs, I only get to keep 1, and so that 9 is going to round that 9 to a 1. Final answer, 1 molal. Good? All right, go ahead and do this one. In the Ed puzzle, it's easier than the last one that we did because we already have moles and we already have kilograms. Go ahead and do this one in the Ed puzzle. All right, so molality is 2 moles of that solute divided by 10 kilograms of that water, the solvent. Our final answer will be 0.2 molal. Good? Good. Another way that we can measure concentration is with parts per million, or I could make parts per billion or parts per trillion, whatever we wanted to throw in there. So basically we're just looking at how many grams of the solute, so I don't have to convert to moles, so grams of the solute divided by grams of this whole solution, and then if it's parts per million, I multiply by a million. If it's parts per billion, then I would multiply by a billion. You get the hint. So let's look at this practice problem together. No amount of lead in drinking water is actually safe, but levels under 5 parts per billion do not cause concern. We know that there is a water crisis in Flint, Michigan. 10% of the homes tested, there was more than 0.000027 grams of lead in every liter of water. We need to figure out if this should make us worried. So we're going to start with our grams of solute, 0.00027 grams of lead. I'm going to divide it by my grams of solution. So I have a liter of water. 1 liter is 1,000 milliliters, and water has a density of 1 milliliter per 1 gram. So if I have a liter of water, I should have just about 1,000 grams of water. So 1,000 grams of water. So 0.00027 grams divided by 1,000 grams of solution. And then to get parts per billion, we're going to multiply by 1 billion, which is 9 zeros. So handy dandy calculator, 0.000027 divided by 1,000 times 1 billion. gives us 27 parts. Whoa, that's a B already. Hold on. Parts per billion. 27 parts per billion, more than 5 times what we are concerned about. So there definitely was an issue, warranted concern with that water and Flint machine that we're still trying to fix. All right. Other ways we can measure concentration, we can look at mass percent and volume percent. So percent by mass, mass of the solute divided by mass of the solution, turn it into a percent by multiplying by 100. 25 milliliters of acetic acid dissolved in 75 milliliters of water. The percent by volume, same idea. We're just looking at volumes instead of masses. So I'm going to take my 25 milliliters of vinegar. 25 milliliters is the volume of the solute. Volume of the solution, be careful. If I'm adding 25 mils of vinegar to 75 mils of water, the volume of my solution is the combination of those two things. 25 plus 75 would be 100 milliliters times 100. To turn it into a percent means that my solution is 25% vinegar. Go ahead and do this one in the Edpuzzle on your own. If you've got 10 grams of sugar dissolved in 50 grams of water, what is the percent by mass of the solution? Use this formula, mass of the solute. The solute is just the sugar. Mass of the solution is going to be the water and the sugar that is dissolved in the water now. So make sure that you add those up before you divide. All right, so hopefully we did. Mass of the solute is 10 grams of sugar divided by the mass of the solution is the combination of 10 and 50. 60 grams times 100 is going to give us 10 divided by 60 times 100. We've got 1.666 repeating. We'll round that to just 1 sig fig, 20% mass. All right, one more little piece and then we are done, my friends. So a dilution, and you should know this already just from the world, dilutions are when we make a different concentration using some other concentration of the source. We're going to calculate the new concentrations by balancing the molarities and the volumes of those two solutions. So let's say that you had like a Kool-Aid mix and you put lots of Kool-Aid and not very much water. It's going to be very, very concentrated. Maybe it doesn't taste very good because it's so concentrated. So you add in some more water, you dilute it. That's what we're looking at now, is this idea of a dilution, adding more solvent to make something less concentrated. We have a formula for that. So molarity formula is here. We're going to skip ionization constant of water for now. We'll talk about that when we get to acids and bases. What we're looking at now is this formula, dilution formula. So volume of solution 1 and the molarity of the solution 1 multiplied by each other will equal the volume of the second solution, the molarity of the second solution. V1M1 equals V2M2. Let's put it to work. V1M1 equals V2M2. So if I have 250 milliliters of 0.10 molar lithium acetate solution, this is a volume, this is my molarity. Since I'm starting with them, I'm going to give them numbers 1. So there's volume 1 and molarity 1. And then I dilute it. So now my new volume is 750 milliliters. Here's my second volume. What will be the new concentration of the solution? So V1M1 equals V2M2. V1 is 250 milliliters. M1 is 0.10 molar. Set that equal to V2 is 750 milliliters. M2 is what I'm solving for. I have not converted my milliliters to liters because they both match. As long as your labels match, they're golden. If they don't match, you have to convert one to look like the other. Let's go ahead and do some algebra here and solve for M2. So 250 times 0.1 divided by 750 should give us M2. M2 equals 0.2 0.033. Lots of repeating decimals, but I'm going to stop here because sig figs mean I get to keep 2. Big M is my answer here. So 0.033 molar is the new solution, the new concentration of the new solution. Good? Good. All right, so go ahead and do this one in Edpuzzle. It's our last problem of the day. If you have 340 milliliters of 0.5 molar sodium bromide solution, what will be the concentration if we add 560 milliliters more water? So be careful with this one. This is not exactly V2 because we added more water to this volume. So think about what is your final volume and go ahead and solve V1M1 equals V2M2. So this was our V1 and here is our M1. V2 is going to be the 560 waters that we added to the 340 that we already had in the solution. Our new V2 is going to be 900 milliliters. 900 is V2. So V1 M1 equals V2 M2. V1 is 340 milliliters. M1 is 0.5 molar. Set that equal to V2 is 900 milliliters. M2 is what we're solving for. Multiply 340 times 0.5 and then divide by 900. Milliliters, top and bottom will cancel out. 340 times 0.5 divided by 900 gives us a molarity of 0.1888 repeating, and I get to keep exactly 1 sig fig, and so my final answer, that 8 will turn that 1 into a 2, and we did it. Our new molarity will be 0.2 molar. All right, we did it, my friends. We talked about solutions, solutes, and solvents. We defined soluble and miscible. These both mean that things will dissolve. We just use soluble for solids and miscible for liquids. We described those factors that affect the rate of dissolving, temperature and pressure, and mixing things and surface area. We reviewed how to use the solubility table when things will dissolve and when they won't dissolve in water. We calculated molarity and molality and parts per million and parts per billion. We looked at percent by mass and percent by volume, and then we wrapped up with that look at dilutions. Good work today.